Next we have exercise 6. You see this function f from the closed interval minus 1 comma 1 into r, and this is the formula defining f. F of x is x divided by x plus 2. We have to prove that this function is 1 1, and also we have to find the inverse of the following function, which is just f. The only difference is that instead of this set, the entire set of real numbers, here you have the range of f. So this new function is both 1 1 as well as on 2, and that is why it will have an inverse, and we will also have to find that inverse. So in the solution we first show that the function is 1 1, that means injective, and for that we take 2 points x1 and x2 in the domain such that the function values at those 2 points are equal. F of x1 is equal to f of x2. This is f of x1, x1 divided by x1 plus x2, and f of x2 is x2 divided by x2 plus x2. And then after doing cross multiplication, you get x1 times x2 plus 2 is equal to x2 times x1 plus 2. And then after that you do the multiplications. That gives you x1 x2 plus 2x1 is equal to x2 x1 plus 2x2. Then you can cancel x1 x2 from both sides, leaving you with 2x1 equal to 2x2. Then after cancelling 2 also, you get x1 equal to x2, and that is why f is 1 1, because same outputs give you same input. That's why. And now we will find the inverse of this function. So this is the inverse function that we are guessing. Okay, we define the inverse function g. I am saying this is an inverse function, that's what we have to show. So g should map the range of f into the closed interval minus 1 comma 1. And the formula for g is this: g of y is equal to 2y divided by 1 minus y. Now we have to verify two things here. The first thing is that for any y coming from the range of f, which is the domain of g, y should not be equal to 1, because if y is 1, then you have 0 in the denominator, and that will not allow you to calculate g of y. So 1 should not belong to the range of f. That is the first thing. And the second thing is that for any y in the range of f, this real number should lie in this interval between minus 1 and 1. Only then can you say that g is really a function, that g is well defined. And then you have to show that g is actually the inverse of f. F means that modified f, where in place of r as the second set, as the codomain, you have the range of f. Suppose there exists, say, y in the range of f such that y is equal to 1. If this happens, then we have a problem with this function. Let's see where this supposition leads us. So then 1 is y, and y is f of x because y is coming from the range of f for some x where in the domain of f, which is this closed interval minus 1 comma 1, and f of x is x divided by x plus 2. But then this is what you are getting, because 1 is equal to x divided by x plus 2, so x plus 2 is equal to x. But this is not possible for any real number x. That's because if this is true, then you are getting 2 equal to 0, which is false obviously, and that is why our supposition is wrong. That means the range of f really does not have 1, the number 1. So there is no danger in taking y from the range of f and using this formula. And next we are going to show that all such outputs for this relation g, I am saying relation because we haven't yet completely shown that g is a function, all the outputs of the relation g lie inside this set. So next what we do, we take any input b in the range of f. This is an input for g. Then because b is coming from the range of f, so b is equal to f of a for some a in the domain of f, which is this closed interval minus 1 comma 1. Alright. Now we apply g on b, and let's see what happens. G of b by definition is 2b divided by 1 minus b, but b is f of a, so we have 2 of f of a 2 times f of a divided by 1 minus f of a. Now f of a itself is a divided by a plus 2. So the expression becomes this, 2 times a divided by a plus 2 divided by 1 minus a divided by a plus 2. Now next, the numerator here becomes 2a divided by a plus 2 and the denominator becomes a plus 2 minus a divided by a plus 2. Now you can cancel these 2a plus 2's, and with that this a and minus a also cancel out, leaving you with 2 in the denominator, and the numerator becomes 2a. And then after cancelling 2, you are getting a, okay, and already a belongs to this, so that's how the output g of b not only can be found because b is never 1, but actually it also belongs to this, and that is why the function g, you can now say that g is well defined, that it's a legitimate function. And now we will show that g is actually the inverse of f. To show that g is the inverse of f, we take any point x in minus 1 comma 1, the domain of f, and then we calculate g composition f of x. By definition this is g of f of x, and by the definition of g, that is 2 times f of x divided by 1 minus f of x. We have just now seen an exactly similar calculation where in place of x we had a. In fact, this is the part of that calculation that is still here. So that ultimately gives you a back. So here also you will get x back similarly. So you see that g composition f is the identity function of this closed interval. Next we have to calculate f composition g. So this next part is also very nice. We can still use this same fact here also. Let's see how. This time we take any point y in the range of f, because we are going to calculate f composition g. So we have to first apply g. So on y we are going to apply g. So we have to take y from the range of f because that is the domain of g. Because y is coming from the range of f, y is equal to f of x for some x belonging to this. You already know, you have seen this 2 times already. Now we straight away go for calculating f composition g of y. Do not write x here, okay, y. By definition this is f of g of y, but y itself is f of x. That means we have this. But g of f of x is nothing but g composition f of x, which is actually x. You have that calculation partly here. So that means this thing is x and f of x is just y. So you are getting y back. That means f composition g is the identity function on the range of f. Combining this fact and this fact, you then conclude that g is actually the inverse of f. And here f doesn't mean the original f, that f which comes after the first step. That means where we have the range of f as the codomain. Next we have number 7, where we have this function f from r into r given by this formula f of x is equal to 4x plus 3. We have to show that f is invertible and we have to find the inverse of f. Because of how we have defined invertible functions, that is those functions which have inverses, if we can find an inverse of f, that would automatically mean that f is invertible. So we will straight away go for the inverse function of f. And in the solution, this is the proposed function that is going to be the inverse of f, which of course, because f maps r into r, g also maps r into r. In this case it's very simple. Both the sets are the entire set of real numbers. And g of y is equal to y minus 3 divided by 4. The difficulty that we had in defining g in the previous solution, we do not have such difficulties here. You are dividing by 4, which is non-zero, and y minus 3 is just a simple polynomial linear expression. So for any real number y, y minus 3 divided by 4 is a unique real number. So already g is well defined. Now these are the two things that you have to show. Show that g composition f of x is equal to x and f composition g of y is equal to y for all real numbers x and y. That's what we did in the previous solution also, right? This part is left to you. Once you show these two things, then g will be the inverse of f.